So last time we talked about Boyle's Law. Today we're talking about Charles' Law. This is just my Uncle Chuck. I like to put him on here. His name's Charles, but we call him Chuck. So Charles' Law is a volume of gas varies directly with Kelvin temperature if pressure is held constant. So pressure is held constant, it won't be included. A volume varies directly with the Kelvin temperature. So if volume goes up, temperature goes up. If volume goes down, temperature goes down. And Kelvin temperature, so you have to make sure you're converting. Pressure we don't care about because it's not included. Volume has to be in liters or milliliters. So the equation for Charles' Law is V1 over T1 equals V2 over T2. Once again, the ones are talking about the original or the initial, so original volume, original temperature, and then the twos are talking about the new or final. I like to tell people if they don't like the division setup to actually just cross multiply. Okay, so cross multiply, and then you get V1 T2, because I'm cross multiplying, equals V2 T1. So you can kind of memorize whichever one works better for you. So let's try it. Oh, real quick visual. So now my pressure is held constant. When temperature goes up, volume goes up. Pressure's not changing. When the temperature goes down, the volume goes down. And notice that direct relationship, a straight line. All right, so let's try it out. A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 degrees Celsius if the temperature remains constant? So we're using Charles. V1 T1 equals V2 over T2. Okay, I'm going to cross multiply them, so I get V1 T2 equals V2 T1. I like to use that one, but it's up to you. Okay, let's make a list. V1 is 752 milliliters. T1 is 25 Celsius, but we have to change it to Kelvin. So we have to add 273. So we get 298 Kelvin. That's what we have to use for the problem. Make sure you're always changing. It says what volume. So V2 is what we're solving for in milliliters. And then T2 is 50 degrees Celsius, but we have to, once again, change it to 270, we have to change it to Kelvin, so we're adding 273. Okay, so I'm solving for V2. I'm going to divide both sides by T1. So V1 T2 all over T1 equals V2. Now I can just plug in V1 times T2 in Kelvin all over T1 in Kelvin. My Kelvins cancel out. I'm left with milliliters. That's going to give me volume. So 752 times 323, all divided by 298, and I get 815.09. Milliliters. So let's check. So Charles says if temperature goes up, volume goes up. If temperature goes down, volume goes down, or vice versa. So what happened to temperature? Temperature went up, it increased. That means volume should go up. Did it? Well, it went from 752 to 815. So yes, it did. So we are good to go. You could also plug everything back into this equation or this equation, and they should equal. All right, let's try another one. A sample of carbon dioxide gas occupies a volume of 5.04 liters at 0 degrees Celsius. What temperature will the gas be if the volume is increased to 6 liters? Notice no talk of pressure because pressure stays constant. So you can use whichever setup you'd like. I always cross multiply it. I just like that format better, but that's me. Okay, now I'm solving for T2. So divide both sides by V1. So T2 equals V2, T1, all over V1. Now let's label. Here's V1 in liters. Here's T1, but I have to add 273. So T1 is 0 plus 273 gives us 273 Kelvin. And then here's our V2. We're solving for T2 in Kelvin. Because you already changed this to Kelvin, it will be in Kelvin when you solve. So T2 is going to equal V2 times T1 in Kelvin, all divided by V1. So 6 times 273, all divided by 5.04, and I get 325 Kelvin for T2. Once again, I like to check. Volume went up. It went from 5.04 to 6. That means temperature should have went up. Did it? It went from 273 to 325. So yes, it did. All right, one more. And as I said before, right now I'm not having you change the units except for temperature. So just be aware that you have to be in liters or milliliters for volume. You have to be in atmospheric for pressure. If you're not, and then always Kelvin. So make sure you're changing that if you need to. Okay, so a helium-filled balloon has a volume of 2.75 liters at 20 degrees Celsius. We have to change that to 200, or I keep saying 200, we have to change that to Kelvin by adding 273. The volume decreases to 2.46 liters after the balloon is placed outside because the molecules get closer together, therefore the volume of the gas decreases. What will the new temperature be? So using Charles' law, cross multiply if you want. You don't have to write the first part if you always cross multiply. It's up to you. Okay, I'm solving for T2. I divide both sides by V1. So T2 equals V2, T1 all over V1. Now I can plug in. V2 is 2.46 liters times T1, 293 Kelvin, all divided by V1. So I get that T2 equals 2.46 times 293, all divided by 2.75. I get 262.1. Check. Volume went down, so temperature should have gone down, which it did. Okay, so that is Charles' law. Volume and temperature vary directly, meaning they either both go up or both go down. V1 over T1 equals V2 over T2. No pressure because it is held constant. Volume must be in either liters or milliliters, and temperature must be in Kelvin.